Please title these notes Geometric Applications Notes, Tangent and Normal Lines, and write the problem that's below. By the end of this lesson, you should be able to write the equation for a tangent line or a normal line to a curve at a particular point. So before we can do anything calculus-wise, we need to make sure that we can write the equation for a line if we know the slope and the point. There are a couple different ways to do this. One is substantially easier in the calculus world, but you need to be able to do both of them. And one is slope-intercept form. So that's this y equals mx plus b. Frequently you'll see multiple choice answers in that form. And the other is what's called the point slope form. Which looks like this. It's y minus y1, so y1 is a number, equals slope times x minus x1. x1 and y1 are numbers. And basically where this comes from, I'm just going to draw it over here, is let's say that we have some sort of line and it's got a slope, and this one down here is y1, or excuse me, x1 comma y1, and this one up here is x comma y. We know that our slope is rise over run, so the distance from y down to y1 is just y minus y1, and the distance in the x direction from x to x1 is just x minus x1. And so this is our rise, this is our run. It's giving us the slope, which is that m. And so you notice if we just multiply both sides by x minus x1, we end up with this form. Totally okay to leave this in this form if you have a short answer question. So let's just look back at our example up here. In this one, I'm going to say this is my x, this is my y. And so I'm going to put each of those in, 8 in for y, the slope is 3/4, x is 2, and then I'm going to have to solve for b and then go and write it as an equation with m and b filled in. So if I go ahead and do that, I've got 8 equals 3/2 plus b. I subtract 3/2 or 1.5 from both sides. b is 6.5, so I can write my equation y equals 3/4 x plus 6.5. That's one perfectly fine way to do it. The other way, using the point slope form, is a little bit simpler for these types of problems. Basically, our y goes in for y1. So there's our 8 right there. Slope goes right here, 3/4. And then we have x minus our x1 is right there, 2. Bam, done. Occasionally you are going to have situations where you see that the answer is in slope-intercept form rather than point-slope form. If so, you just do some distribution, do some combining of like terms, and you end up with it looking the same. Let's do a quick demo for this one. So we're going to do y minus 8, distribute that 3/4, 3/4 x minus 3 times 2 is 6, 6/4. Y equals 3/4 x minus 6/4 plus 8. And when I simplify that out, I get the same thing that I did over here. So this is the basic mechanics of what we're doing. All we're going to be using calculus for is to figure out what the slope is of the line that we're working with, and occasionally to figure out what the points are. So let's get into the meat of this. Finding the equation of a tangent line at a given point. So here's the number one thing to know. The slope of a tangent line is the value of the derivative at that point. Remember, this is one of our definitions of the derivative, is as the slope of the tangent line, or the instantaneous rate of change. So if you're looking for a tangent line, your slope is right there, coming out of calculus. This is going to be our m, and then the point is generally given. So let's go ahead and do a problem. Find the equation of the line tangent to y equals 3x minus cosine x, whoop, right there, at the point 0, -1. The vast majority of the time this is going to show up in a non-calculator question, so let's do this without the calculator. The first thing that we need for the slope of the tangent line is to take the derivative of this. So I'm just going to call this y. I'm just going to change that name to f of x, just for consistency with our notation. So I'm going to let f of x equal 3x minus cosine of x. I'll do the derivative. Derivative of 3x is 3. Derivative of negative cosine x is negative sine x. And now I want to find the equation of the, I want to find the slope of the tangent line at this particular point. So that just means I'm going to find the value of the derivative, not in general, but specifically at that point, specifically when x equals 0. So f prime of 0 is going to be 3 minus the sine of 0. This is something you really want to kind of just know by now. But sine is the y value, sine is 0. So f prime of 0 equals 3 minus 0, f prime of 0 equals 3. Make sure you're clear about what you're being asked for. This is not our final answer. This is the first step to finding the equation. This is our slope, so we can use it. I'm going to use the point slope formula over here because it makes life way easier. Y minus y1, which is -1, equals slope, which is 3, times x minus x1. And there we go. A similar problem asks us not to find the equation of the tangent line, but to find the equation of what's called a normal line. That is an R. My handwriting strikes again. And the normal line is perpendicular to the tangent line. And there are a lot of useful things that it's used for later on in mathematics, but for now we just kind of want to know the general idea of it. But what the really key thing is here is to know that a perpendicular line has the opposite reciprocal slope to the other line. So that means the normal line's slope is the opposite reciprocal of the tangent line slope. So that means if the slope of the tangent line is a over b, then the slope of the normal line is negative b over a. Other than that, it's pretty much exactly what we just did. So let's do our second problem. Find the equation of the line normal to y equals 3x minus cosine x at the point (0, -1). So again, we're knowing that the derivative of this at the point 0, -1, that is going to give us the slope of the tangent line. If we do the opposite reciprocal, we'll get the slope of the normal line. So to find the slope of the tangent line, so I'll rename it f of x again, just so that I can clearly note that I'm evaluating it. F prime of x is 3 minus sine of x. F prime of 0, same problem we did before. This is the slope of the tangent line. And what that means is the slope of the normal line is the opposite reciprocal, so -1 over 3. In these examples that I have for you today, I think pretty much all of the slopes of the normal lines are negative. They don't have to be, it's just the opposite of whatever we got up here. So what we're going to do then to find the equation is exactly what we just did. We're going to use this as our slope, -1/3 is our m. We're going to do y minus y1, and then x minus x1, like so. So that's finding the equations for the different lines. The reason that we want to do that sometimes is for the following reasons. It's useful for doing approximations. So let's title this next section Approximations. And here's the idea. If we have a curve, it might be difficult to find a value on the curve for a given x. Like let's say we're trying to evaluate without a calculator, the square root of, whatever, 15. I don't know. So the thing is that if we have the equation for the tangent line, then we can approximate the value of a curve by finding the value of the tangent line that's really, really close to it. So I'm just going to write down a little explanation, and then we're going to talk about it some more. Now with the calculator this becomes largely obsolete, but it's still good to know where this stuff comes from. nice thing about the tangent line is that because it's a linear function, we're almost always able to evaluate it pretty easily, and that's not always true for some really funky things. So like, let's say that we had a curve that sort of looked like this, and notice we have no idea necessarily like what that is or what equation it models or whatever. It might be really, really hard for me to actually find this point right here. But if I have a tangent line that's drawn at a nearby point, I'll do the tangent line in pink, then what I can do is I can find this point instead. And really what's going on is that even though this might not be exactly the point that I'm looking for, it's probably pretty darn close. And it's at least enough to give me a general sense of what this point is going to be. This is especially useful when mathematicians were finding zeros, so specifically where this crosses the x-axis. And just like where we would use the zeros command on our calculator, they would set up a little tangent line and say, okay, you know, where is this approximately going to be crossing the x-axis? Let's use that point. It's as close as we're going to get. So let's look at a problem for this. If f of x is twice differentiable, and f of 3 equals 9, f prime of 3 equals 2, and f double prime of 3 equals -1. Approximate the value of f of 3.1 using the line tangent to the curve at x equals 3. So if you notice with this problem, we actually don't even have an equation. We don't know anything about what f is doing when x is 3.1, but we do have enough information to figure out what the equation of the tangent line is. And notice there's some extra information included here. This is very useful information. It's giving us the point. This is our x, this is our y. And this is very useful because this is giving us the slope of the tangent line. Notice this is completely a distractor. We're not going to use f double prime, so don't be thrown off by it. Sometimes they do that. Just put in extra information just to trip you up. So what we can do is we can do the equation of the tangent line. And what we're doing is we're doing y minus y1, which is 9, equals the slope, which we just said was 2, x minus x1, which is 3. So y minus 9 equals 2x minus 6, add 9 to both sides, -6 plus 9 is 3. Now remember, always look back at what the question is asking for. It's asking us to approximate the value of f of 3.1. So we don't have the equation for f, but we do now have the equation for the tangent line. And what we can do is we can just plug 3.1 into here to get our approximation. And that's sort of our best guess for what f of 3.1 would be. What this is particularly used for is problems like the following. If f of x is a differentiable function, remember differentiable means we can take the derivative, such that f of 7 equals 1 and f prime of 7 equals negative 1, use the tangent line of f of x at x equals 7 to find, an approximation to a 0 of f of x. Remember, a 0 is the the x-intercept, where y is equal to 0. And the thing is, we don't know where f has an x-intercept. In fact, I have no idea what this is even doing. I mean, it could be some sort of like a weirdo squiggly thing. But what I do know is that I do know that there is a point 7, 1, and it has a tangent line, and the slope of that tangent line is negative 1. So what I can do is, even if I can't figure out where this 0 is right here, I can figure out where the tangent line has a 0 right there. And that at least gets me in the right general ballpark. So what we're going to do is we're going to start off by saying we're going to find the equation of the tangent line, and we're going to figure out when y equals 0, what's the value of x on the tangent line. So equation of tangent line y minus y1, so here's our y point, and here's our slope, x minus x1, and now what we're going to do to approximate is 0. We're going to set y equal to 0. So 0 equals negative x plus 8. There we go. That's our approximation of the 0.